Hey everybody, Dr. A here, and in this video we're going to be exploring an example of analyzing a statically indeterminate truss. And we're going to be using what's called the force method, which is also sometimes called either the redundant method or the compatibility method. So let's go ahead and get started. In the given information, we're being asked to determine the force in member BD of the truss below. We're also being told that AE, which is called the axial rigidity, is constant for all the members. So in our truss here, we have 6 members, okay? We have this kind of box or rectangular shape exterior, and then we have 2 diagonal members. Now, one thing to note is that this right here is an overlap. This is not a joint here, okay? So you have one solid member AC, and then you have another solid member BD, and in fact, BD is what we want to find the force in. The horizontal dimension of this box-shaped truss is 3 feet, and the vertical dimension is 4 feet. We have an external pin at A and an external roller at B. And notice at point D, joint D up here, we have a horizontal applied force of 5 kips applied to the right, and then we have a vertical downward applied force of 7 kips. Okay, so let's go ahead and get started. Now that we know what we're looking at, one thing we want to note in our solution is that this truss is statically indeterminate to the first degree, and specifically it's what's called internally indeterminate. So what do we mean by that? Well, first we notice that the number of external reactions is 3, okay? We have an AY, an AX, and a BY, so R equals 3. And then clearly we can count the number of members, and we see that M equals 6, all right? So now we can say R plus M equals 9, and then we can compare this to 2 times the number of joints. There's 4 joints here, so 2J is equal to 8. And so clearly the degree of indeterminacy is 9 minus 8, which is the first degree. And more specifically, this is statically indeterminate because of the internal aspects of this truss. So we can call this internally indeterminate. Okay, and again, the reason why is because when you look at just the external support reactions, you have 3 external reactions, AY, AX, and BY. So you could go ahead and solve for AY, AX, and BY using basic equilibrium equations. No question about that. But the reason why this is statically indeterminate is because you have an additional member somewhere in this entire truss that is not necessary for static equilibrium and stability. And hence the name redundant, okay? We have an extra member that is a redundant member, okay? And specifically, what member would be considered the redundant member? Well, in order for us to develop a primary structure that is stable, we're going to need to take one of these diagonals as the redundant. Now, if you watch the background video, what we typically do is we declare the member that we want to find the force in as the redundant. So whenever a problem says determine the force in a particular member, and you have a statically indeterminate system, it's generally best to take that member to be your redundant, okay? So here's what we're going to do. We're going to flip the page, and we're going to take the force in BD as the redundant, okay? And from this, what are we going to do? We're going to generate 3 different systems that we're going to relate together, okay? So we need to first analyze what's called the primary system, or in this case, we can call it the primary truss, by removing the effect of FBD. Then we will analyze the redundant truss, really by analyzing what's called the unit load truss. And we will relate these together by a compatibility equation. Okay, so if this is sounds kind of unfamiliar to you, take a look at my couple of background videos on the force method and another background video on the force method as it pertains to trusses. Okay, so let's go ahead and get started with developing these systems. First, let's go ahead and develop this primary truss. Okay, so I'm going to sketch this over here. So I've got this primary truss that I'm drawing here. Okay, now this primary truss is going to be kind of similar to the original truss, okay, with the exception of we are removing the effect of that member BD, okay? So I'm still going to have, you know, a pin at A and a roller at B, okay? And this is still 3 feet and 4 feet, and, you know, this is joint C, this is joint D, you know, and then we have A and B. But instead of having the member BD, what I'm going to do is I'm going to, like, cut that member, okay? And I'm going to do such that, that its effects to be able to sustain a force are removed, okay? So when I do that, I'm going to develop kind of like a relative displacement in between B and D. And so I can draw that by doing this. I can project maybe some dimension lines here, okay? And I'm going to put, you know, a dimension line here. And we call this displacement delta BD. That's capital delta BD. Now, what else is on this primary truss? Well, your real loads are still going to be there. You're still going to have your 7 kips here and your 5 kips here, okay? And so if we want to, you know, label this accordingly, we're going to call this the primary truss, or primary system is where you might also hear it called that. Okay, now we also need to develop the redundant truss. Now, what does the redundant truss look like? Well, geometrically, again, it's going to be kind of similar to both the primary truss and the real truss from the beginning. Okay, so we're going to draw this out here. And your redundant truss is still going to have, you know, a pin at A and a roller at B. It's 3 feet horizontally, 4 feet vertically. Okay, and this is point C and point D here. But the big difference here is in your redundant truss, you are going to have a force within BD. Okay, so the way I draw that sometimes is going to look kind of like this. I'm going to have this force here, and I'm going to show a little zigzag here, and I'm going to also show it in the opposite direction coming out of B as well. And I put these little zigzags here just to show a gap there. And so this is going to be, you know, the force in BD. The force in BD. Now, what is this this kind of gap or distance here between these cut marks? Well, this is going to be what we label capital delta BD BD. So double subscript notation, and we talked about this in one of our, or both of our background videos probably. So the double subscript notation means that this is the relative displacement between joints B and D due to a redundant force in that member BD. Okay, so again, that's a double subscript BD BD. All right, now again, we're going to call this the redundant truss. Okay, now am I done here? No, I need that third system that's really important for us to analyze, and that's called the unit load truss. So again, I'm going to draw a third truss here that is going to be geometrically similar to the other systems that I'm dealing with for this problem. Okay. And in particular, this unit load truss that I'm sketching right now is going to be very, very similar to the redundant truss that I just finished sketching. Okay. So again, this is going to be called the unit load truss. All right. Now, the big difference between the unit load truss and the redundant truss is that instead of FBD going through this line of action, I'm going to have my unit load going through that line of action. Okay. So watch what I'm going to draw here. I'm going to draw kind of a similar zigzaggy pattern here. Draw it a little bit better. Okay. And then it's also going to radiate from point B. And I'm going to draw some, vector heads here. Now, again, instead of FBD radiating from these, I'm just going to have that unit load of 1. And more specifically, it's a dimensionless unit load, okay? So it's not 1 kip, it's just 1 nothing, okay? And, also my dimensions of 3 feet and 4 feet tall are still there. And I'm going to also have, this displacement that I'm measuring here. Now, what do we call this dimension line here? Well, this dimension line here is going to be little delta BD BD, okay? So this is what we sometimes call the linear flexibility coefficient. And again, I provide some background information on this context, in some previous videos, okay? So we relate these three guys together by our compatibility equation, okay? So what does our compatibility equation tell us, okay? So the compat equation relates these displacements together. Specifically, we're going to say delta BD, which is from the primary truss, plus delta prime BD. This should be a prime, by the way. I think I forgot to sketch that on there. This is delta prime BD. Delta prime BD equals 0. Okay, now where do we get this idea from? Well, remember, the real original system back here in the problem statement has, this displacement here, or this member here, okay? And so realistically, the displacement between B and D should be locked in. It's really separated by, this diagonal member, okay? Which is 5 feet long, So the way we set up this compatibility equation is we say the displacement in the primary truss, delta BD, superimposed with or added with the displacement in the redundant truss, delta prime BD. When you add those together, you should really get a net 0 displacement. Okay. Now, if you recall from our background video, how do we relate the redundant truss and the unit load truss? Well, we relate them by scaling this delta prime BD with little delta BD. Okay. And again, these two are related really by a scale factor of the magnitude of this force. So the way you can think about it is if a unit load of 1 causes little delta BD, then how can I relate that to a force of capital FBD causing delta prime BD? And the way we can write that or express that is the following. We'll rewrite this compatibility equation as delta BD plus FBD times little delta BD equals 0. So what I'm saying here is that delta prime BD will equal FBD times little delta BD. Again, these are proportional, and that's why we call this little delta the linear flexibility coefficient. Now watch what I can do. I can rearrange this form of the compatibility equation, and I can say, hey, FBD, which is the force I'm looking for ultimately, is going to be equal to capital delta BD divided by little delta BD with a negative out in front. So all I did here was I took this version of the compatibility equation and I algebraically solved for capital F BD. Okay, so what do we do here with this compatibility equation? Well, in order to evaluate this and get ultimately what we're looking for, capital FBD, we need to get two displacements. We need to get this capital BD and we need to get this little delta BD. Okay, so what we need is this delta and then this little delta. So let's flip the page and write a sentence here on how this is set up. We're going to say we're going to use virtual work to compute capital delta BD in the primary truss and then to compute little delta BD in the unit load truss. So what have we kind of set up here? Well, what we're saying is we're actually going to use virtual work 2 different times. So really this kind of problem becomes like doing virtual work 2 times. It's really like 2 virtual work processes kind of lumped together into one problem. Okay, so let's do this one at a time. All right, so I'm going to change colors here. I'll tell you what, I'm going to make this purple. I'm going to say in this first part, I'm going to say primary truss analysis to get delta BD using virtual work. Okay, so that is what we are about to do right now. We're about to do a virtual work process on the primary truss to get capital BD. Okay, so here's what I'm going to do now. Whenever I do virtual work, what do I have? So forget about everything else. Let's just zoom in here and think about virtual work. Whenever I do virtual work in a truss analysis, I'm going to have a real system and a virtual system. Okay, so the first thing I'm going to do is I'm going to say, hey, let's draw the real primary truss. Okay, so here's what I'm going to do. I'm going to go ahead and draw out what is the real primary truss. Okay, so the real primary truss is still going to have that pin and roller, 3 feet, 4 feet, and the real primary truss is going to have those real loads, 7 kips and 5 kips. And so again, let's label this real primary truss. Okay. All right, now what about that member BD? Okay, so remember I've got, this is point A here, point B, point C, point D. What about that member BD? Well, remember we made a little cut here and we said that, this is not going to sustain a force here, okay? So this is going to have a force of 0 in it. All right, so it's almost like it's not there. Okay, you can almost think of this member BD as not even being there. In fact, some references and textbooks won't even draw anything for BD. They'll just leave this out completely. Okay, I like to put this little squiggle there to remind myself that it used to be there, but we've cut it. And so if you cut this thing, it cannot sustain a force within it. All right, so now I'm analyzing the real primary truss. Now, what do we get from the real primary truss? I'll put a note here. I'm going to say to get capital F member forces. Remember, right now we need to think of this as just virtual work, okay? So I'm going to use method of joints to get those capital F forces at this stage. All right, so I'm going to start with joint D, and I can draw a free body of that. I'm going to have capital F AD. I'm going to have capital F DC. I've got 7 kips here. I've got 5 kips here. And then clearly from equilibrium, we see that FDC will end up being negative 5 kips, and FAD will end up being negative 7 kips. And those would indicate compression, okay? So joint D is kind of an easy one to analyze. And remember, there's no force coming out here diagonally, okay? That's 0. All right, where do I go next? I'm going to go to joint C next. So let's go to joint C. And over at joint C, I'm going to have capital F BC. I'm going to have capital F AC, and this is at, a 3-4-5 ratio. And then I have that 5 kips here. Where is this 5 kips coming from? Well, that's the FDC in compression coming at C right there, okay? And so here, again, doing a method of joints equilibrium process, we'll say sum of the forces in the x direction equals 0. And so we'll have 5 kips minus FAC times 3/5 equals 0. And so we'll do a little rearranging, and we'll get FAC is 8.33 kips. That'll be positive or in tension. And then I'm going to say sum of the forces in the y direction equals 0. And I'll write negative FBC minus 8.33 kips times 4/5 equals 0. Do a little rearranging, and I'll get FBC is negative 6.67 kips, which really means that FBC is in compression, okay? Am I done? No, but I'm getting there, right? I can check off, put little check marks here by these members where I've calculated the forces. Finally, I need to do method of joints one more time at joint B. So I'm going to come over here. I'm going to say joint B, free body diagram. And so, at joint B, of course, I'm going to have a BY. I'm not really interested in BY, though. I am interested in FAB, capital FAB. And I know that FBC is here in compression, 6.67 kips in compression. Now, do I have this diagonal? Is FBD going to show up here? No, not really, because remember, it's 0, so it's like it's not there. And so, obviously, you look at this, and FAB equals 0, okay? So these are my capital, one more time, these are my capital F forces in this real truss for the primary system, okay? Doing virtual work, all right? What do I do next? Well, next I'm going to analyze the primary truss in order to get little delta, okay? I'm sorry, not little delta, the little f forces, okay? The little f forces. So how do I do that? Well, we called this the real primary truss. Now I'm going to scroll over, and I'm going to say, hey, I'm going to draw the virtual primary truss, okay? The virtual primary truss. So what does a virtual primary truss look like? Well, that virtual primary truss still kind of has this rectangular shape, and I still have a pin and a roller. I have AC there, so I can label these, in fact, with little letters A, B, little C here, little D here. This is 3 feet, this is 4 feet. This is going to be the virtual primary truss. And so what do I do? What am I going to get from a virtual truss? Well, I'm going to put a note here. I'm going to say to get the little f forces when I am using virtual work. Now, what do I do with BD in this virtual truss? Well, what I really need is a unit load here, okay? I need a unit load, so I'm gonna do this little zigzag here, and I'm gonna get this unit load of 1 kip. I'm going to put that inside of BD, okay? And so again, remember, forget about this being statically indeterminate for a second. What we're doing right now is just virtual work. So if I'm trying to get that relative displacement, capital delta, between B and D, then I'm doing virtual work. I'm getting the capital F forces, and I'm getting the little f forces. The little f forces here are coming from the fact that we are finding a delta between B and D. So I put a unit load of 1 kip in that direction. Okay, so review virtual work if you're a little rusty on that concept. So here I'm going to do method of joints to get the little f forces. So I'm going to start with joint little d. Okay, draw that a little bit better. And so when I analyze joint little d, I'm going to have a little f CD, I'm going to have a little f AD, and I've got 1 kip here, and this is a 3-4-5 ratio. And so here I can say sum of the forces in the x direction equals 0. So I'm going to have little f CD plus 1 kip times 3/5 equals 0. Little f CD is negative 0.6 kips. And then I'm going to sum forces in the y direction. And I'm going to say negative little f AD minus 1 kip times 4/5 equals 0. So little f AD is going to equal negative 0.8 kips. What am I going to do next? Well, next I'm going to go to joint C. Okay, I'm going to come over here. I'm going to say let's do a method of joints operation at C. So at joint C, I've got this 0.6 kips coming into C. I've got little f BC. I've got little f AC. I've got a 3, 4, or 5 slope. And so here I'm going to say sum of the forces in the x direction equals 0. So I've got 0.6 kips minus little f AC times 3/5 equals 0. Little f AC is going to be a positive 1 kip in tension. And then sum forces in the y direction equals 0. And summing force in the y direction, I'm going to have minus 1 kip times 4/5 minus little f BC equals 0. Little f BC equals negative 0.8 kips. Okay, and so what I've done is I'm chipping away at finding these little f forces. Okay, finally I need to go to joint B. I need to go to joint B. And draw a free body of that. I've got a little by here that I'm not really interested in, but I am interested in this little FAB. I've got 0.8 kips coming in compression. That's actually from BC. Okay, so this 0.8 kips right here coming into joint B is from this little FBC. And then don't forget, what about the force in BD? Well, remember that's 1, okay? So this force right here is this unit load right here, 1 kip, okay? And so we're going to write the slopes here, 3, 4 slope, and we're going to do a method of joints operation. So we'll say sum of the forces in the x direction equals 0, and we're going to say negative 1 kip times 3/5 minus little FAB equals 0. So little FAB is going to equal negative 0.6 kips. Now I have all my little f forces. And remember, right now, this is really just a virtual work type of process, all right? So let's scroll over, and I'm going to say let's make a table to help us get capital delta BD. So make a note here. Make a table to help us get capital delta BD using virtual work. Okay, so how did we do this when we first learned about virtual work? Well, what we did was we made kind of a nice size table. All right, and we called this member. All right, and then we maybe had a column for the length in feet. And then we had a column for the capital F forces in kips. And then we had a column for the little f forces also in kips. All right, and then we made a column for FFL, and that's going to have units of kips squared times feet for us. And so let's just populate this table. Our members are AB, BC, CD, AD, AC, and BD, okay? And then those lengths are 3 feet, 4 feet, 3 feet, 4 feet, 5 feet, and 5 feet. So you can double check me, maybe pause the video and look back in your notes and make sure you're getting the same values I'm getting. Our capital F forces are 0 kips for AB, negative 6.67 kips for BC, negative 5 kips for CD, negative 7 kips for AD, 8.33 kips for AC, and then 0 for BD. Our little f forces that we just got are negative 0.6 kips for AB, negative 0.8 kips for BC, another negative 0.6 for CD, another negative 0.8 for AD, and then 1 and 1 for AC and BD. And then if I multiply across to get the FFL terms, then I'll get the following. I got 0, 21.3, 9, 22.4, 41.7, and 0. So this would be a great time maybe to pause the video and crank out these calculations on your own and make sure you're getting the same thing I'm getting. Don't just trust me. Make sure you're getting the same thing I get, okay? So when you evaluate this, what we can do is sum these values in this column, okay? And if I say sum of these values, I should get 94.4 kip squared feet. Now, this is a good refresher on virtual work. What's the virtual work formula tell us to do? It says take 1 kip and you multiply it by delta BD, and that's going to equal the sum as I goes from 1 to n. In this case, n is 6 because we have 6 members of little f capital FL over AE sub I. And so that FFL part of the summation is this 94.4. That's why we make the table, to help us stay organized. Now, our problem at the very beginning, what did it say about the axial rigidity? It said AE is constant for all members. So this is just going to be written as 94.4 kips squared times feet. And this is all going to be on top of AE, okay? Now, if you divide both sides by 1 kip and 1 kip, what are you left with in terms of delta BD? Well, you'll have a delta BD is equal to 94.4 kip feet over AE, okay? Now, am I done? Nope, but I got a big part of it done. I mean, this is part of what we need for that compatibility equation. Now what do? Now I've got to use virtual work and do this all over again, but but for the unit load truss. Now, don't close out of the video yet because I got a cool surprise for everybody, okay? So let's turn the page and let's write this down so we understand the process. We're going to use virtual work again to compute little delta BD in the unit load truss. Okay, and so let's be organized. Okay, I'm gonna say in purple here, unit load truss analysis to get delta BD using virtual work. Okay, so I'm gonna start out going through the same process I did before. Now, here is what's really cool about this. We're gonna discover that the unit load truss analysis to get little delta using virtual work, we've actually already done a lot of that work in some previous steps. Let's investigate why. Let's remind ourselves, what does the unit load truss from the force method look like? I'm going to scroll back several pages. What does that unit load truss look like? Well, that unit load truss is right here. Look at this. It has a 1 going through member BD, no real loads. So the unit load truss looks a whole lot like what? It looks a whole lot like the virtual primary truss that we already analyzed, okay? So watch what I'm going to do here. And again, I'm kind of drawing this out because I really want us, it's really important to me that we understand what's going on. This unit load truss, the real unit load truss, is going to look like this. Okay, here's this. And again, I know we're drawing these trusses a lot. Okay, the real unit load truss is going to have that 1 right here, okay? Dimensionless, right? Dimensionless. It's 1, nothing, okay? So this is going to be A, B, C, D, okay? And again, this is the real unit load truss. All right? And this is based on a dimensionless unit load. Well, guess what my capital F forces are for this? Capital F AB is negative 0.6. Capital F BC, negative 0.8. Okay? Capital F CD, also negative 0.6. Capital F AD, negative 0.8. Capital F AC is 1, and capital F BD is also 1. So these capital F forces in my real unit load truss are numerically the same as the little f forces that I got in my virtual primary truss because it's loaded the same way and it's geometrically identical. Okay, the only difference is you got to remember the unit load truss when we're doing the force method, the redundant method, is based on a dimensionless unit load. So it's just a 1 here, no kips attached to it. Okay, now what about the virtual unit load truss, right? A lot of stuff going on here. What about the virtual unit load truss? So our virtual unit load truss guess what also looks pretty much the same as the real unit load truss, except here I do have one kip here. So this one does carry units of kips. And the reason why this carries units of kips is because this is, again, our virtual unit load truss, and this is based on a unit force of the units we're dealing with. Okay, so in this case, kips. So I'm gonna label these. These are actually lowercase letters, right, from virtual work: A, B, C, D. So what are these little f forces now? Well, this is going to be little FAB is negative 0.6 kips. These do carry units now. Little FBC is negative 0.8 kips. So same as what I just wrote. I'm having trouble writing this. My palm keeps activating something else, even though I thought I turned off the palm sensitivity. Little f CD is negative 0.6 kips. Little f AD negative 0.8 kips. Little f AC is 1 kip. Little f BD also 1 kip. Okay. Now am I done? I'm so close. I'm going to make another table, another virtual work table, just for the unit load truss analysis, okay? So, I'm going to draw out this table. All right. I'm going to have the member. I'm going to have the length. I'm going to have capital F forces. I'm going to have little f forces, okay? So, member, length in feet, capital F, little f forces has kips, and then I'm going to have little f, capital FL, which is going to carry units of kip feet, because remember, the capital F forces don't have units, okay, for this particular truss. AB, BC, CD, AD, AC, BD. Okay, and let's write these lengths: 3 feet, 4 feet, 3 feet, 4 feet, 5 feet, and 5 feet. Negative 0.6, negative 0.8, negative 0.6, negative 0.8, 1, and 1. And then I'm going to repeat this over here: negative 0.6, negative 0.8, negative 0.6, negative 0.8, 1, and 1. And then if I multiply across here and get FFL, then I'm going to have 1.08, 2.56, another 1.08, another 2.56, and then a 5 and a 5. Okay? And so finally, well, almost finally, not quite finally yet, I can say 1 kip times little delta BD equals the sum as I goes from 1 to 6 of FFL over AE. And I'm going to sum these down, okay? If I sum these down, I'll get 17.28 kip feet. And so this is 17.28 kip feet over AE. And I'll see that the 1 kip cancels over here. And so I'll get little BD as 17.28 feet over AE. Okay, am I done? Oh man, I'm so close. I'm so close. This is really important. Now I've done virtual work 2 times, okay? And I'm going to put these 2 pieces together in that compatibility equation, okay? So what did that compatibility equation tell us from the very beginning of this video? Capital FBD is equal to negative delta BD over little delta BD. And so if I substitute my values in there, I'm going to get a negative 94.4 kip feet over AE divided by 17.28 feet over AE. And I can clearly see the AEs cancel, the feet cancel, and so finally I'm going to get an FBD equals negative 5.46 kips, which means that FBD is going to be in compression, 5.46 kips in compression. And this is my final answer, okay? Now, you might be thinking, geez, Dr. A, this was a long video. This was a lot of hand calculations. Am I always going to have to do this by hand in real life if I become a structural engineer? The answer is no. Vast majority of the time in structural engineering, you're going to use software to help you perform these analyses automatically, and it's going to be much, much faster. In fact, I used a software package called eTabs by a company called CSI, Computers and Systems Incorporated, to check myself. So I put this in a software package, and I confirmed that this is the correct answer, and it took me, less than a minute, okay? So why do we have to learn this by hand? Well, we have to learn these methods by hand for a few reasons. Number one, you need to understand structural behavior. And you can model things in a computer all day long, but if you don't really understand the behavior of structures and how and why these things work, then the computer models are junk, right? So as an engineer, you have to understand why and how this works, okay? Then you can go to a computer model, because then you're going to have an understanding of how and why the model is working. And if it's not working, you can figure out what's wrong with it, okay? The second couple reasons is that this still could show up in some form or another on your FE exam or PE exam. So the FE and the PE exams expect you to have a fundamental understanding of this concept, which is the other reason why we still teach this, okay? Now, last piece of information. Does it make sense that this member is in compression? If I go all the way back to the original indeterminate truss, if I look at how these applied loads are acting at joint D, does it make sense that BD should be in compression? Yes, if you just look at what's physically being applied, it does make sense that BD is in compression. Okay, so that concludes this video. Again, our final answer is 5.46 kips in compression. Thank you so much for hanging in there with me for this long video. And please don't forget to like and subscribe and be on the lookout for other content like this.